The main idea of my Lab 5 project was to find the kinetic energy of a golf ball being thrown through the air and use that data given to me by VPython to find the potential energy of the ball and when it is at its maximum. So in this coding, we'll be using multiple equations, mostly involving Newton's second law and the energy principle. Here we have that the kinetic energy is equal to 1/2 mv squared, and the potential gravitational energy is equal to the mass times gravity times height. We will also be including other equations such as the drag force, which is equal to the proportionality constant times the magnitude of v squared, the net force, which is going to be equal to the drag force plus the weight force. The weight force is equal to the opposite of mass times gravity. We'll also be using the actual Newton's second law formula. Final velocity is equal to the initial velocity plus the net force divided by mass times delta t, and the y position is equal to the initial y position plus the average velocity times delta t. All of these will be relating to the j hat vector in the y position. So when we go to my tracker video, we watch as the golf ball goes up in the air. It starts out with an initial velocity of 3.636 meters per second, calculated by finding the change in time the change in position over the change in time. And we see that as it approaches almost 0.65 meters in the air, it reaches a speed of about 0 and falls back down to my hand. So when we take this data and put it in our tracker, or VPython coding, we put in our initial conditions into the Python coding that matches the data of my golf ball. So that the mass is 0.045 kilograms. The initial velocity that we found earlier is 3.636 meters per second in the vertical y position. We use in delta t a gravitational constant, 9.8 meters per second squared. We find a proportionality constant b by using multiple trial and error functions to find the correct slope and final position of the ball. We insert our kinetic energy equation, 1/2 mass times velocity of the ball squared. We do all of this under the time step 0.768 seconds because that's how long the golf ball is in the air. We install the drag force, which is equal to the j hat times the magnitude of the drag force, where the magnitude of the drag force is equal to the b, the proportionality constant, times the velocity of the ball squared. We install the weight force, which is the opposite of the mass of the ball times gravity times the j hat vector, and we install the net force, which is equal to the weight force plus the drag force. We also install Newton's second law and the position found by using Newton's second law, and we put it in our kinetic energy equation one more time. So when we run our model, we see that the yellow arrow is the constant gravitational force acting on the ball as it moves through the air, while the blue line represents the position of the ball as time goes to 0.768 seconds. We see that it reaches a maximum height of about 0.65 meters, which is almost identical to that of the tracker data. And we see that the red line models the kinetic energy of the equation. It starts out as non-zero because it is being calibrated right after I release the ball at its first instant. And when it reaches a maximum height, when the ball reaches the maximum height, the kinetic energy is found to be 0. This is because at the very top of the arc, the ball, for one single instance, has a 0 velocity. So therefore, by using the equation 1/2 mass times velocity squared, the velocity squared is equal to 0, making the whole kinetic energy at that instant equal to 0. So when we plot this against the actual experimental position found by using tracker, we see that the experiment position almost identically matches with that of the model position. The red model position is only slightly higher and a little bit more smooth than the experiment position, but that is most likely due to human error in miscalculating the actual position of the center of mass of the ball. Now, to address our final question, when is the potential energy of the golf ball the greatest? This is going to be when the kinetic energy is the least amount possible, because the potential energy and kinetic energy between equations usually oscillate, especially in a system like given here with the golf ball moving through the air, where the only forces acting upon it are my hand and the force of gravity. So the potential energy of the ball is at the greatest when the kinetic energy is equal to 0, which here, given by the VPython data, is about 0.374 seconds after the ball was released into the air. This is given by the energy principle, which says that delta E, the energy of the system, is equal to delta K, the change in kinetic energy, plus delta U, the change in potential energy. So if E is equal to 0, it means that the opposite of K is equal to U, or that the opposite of U is equal to K. So this means that if K is very high, U is going to be very low. And this is the case in this situation. So when K is equal to 0, the kinetic energy, that means the potential energy is going to be at its greatest.